In this next section, we're going to talk about what's called a titration, which is an experimental technique used to find the concentration of either an acid or a base. Okay, so what I've got here is I've got two different things on the screen. I've got a beaker full of water, and then on the right hand side, I've got a graph of what's going to be a pH, what's called a pH curve. Okay, so in a titration, what you do is you have a solution of a known concentration. So let's say I'm going to take a weak acid. Let's say it's 0.125 molar HNO2. Okay, and I've got oh no, sorry, that's actually backwards. Let me back up. Okay, let's just say I've got a solution of unknown concentration of HNO2. And HNO2 is a weak acid. And actually, even to make it easier, just so I don't have to write as many letters, I'm just going to call it unknown concentration of HA. And HA is therefore a weak acid, which means it creates an equilibrium system. So you got H plus and A minus, okay? But as you know, most of what's in that solution, because it's a weak acid, is what's called the molecular form, okay? The non-ionized form of that acid. So therefore, what do you have floating around the water? Well, you mostly have a bunch of HA molecules. Okay, and you're going to have a little bit of H pluses and A minuses. But again, even that relationship is not very good compared to how many there are all total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So there's a certain number of acid particles in that water solution. And what you do is you use called a burette. And you use a burette, and little by little you start adding. In this case, we're gonna have a burette filled with NaOH, a strong base. So this is going to be a weak acid, right? HA, strong base titration. So in this reaction, what's going to happen is think about the chemical reaction. We're going to have some HA. We're going to react it with NaOH. And like in every acid-base reaction, like one of our previous videos, it's going to make water, H2O. So the H goes with the OH, and then the Na goes with the A. Now, the Na, anything with a sodium is going to be soluble. So really, over here, the Na plus is going to cancel out, and you're going to be left with the OH minus. And then the Na plus on this side is going to cancel out. You're going to be left with the A minus. Okay, so really, the net ionic equation looks like this. We just take out the sodium ions. Okay? So as we start to add some of that sodium hydroxide, the sodium hydroxide is going to react. And again, I talked about this in the previous video. It's going to react with the easiest thing it can. So if it can react with the H pluses and the A minuses and get rid of those ones right away, it's going to, because those are already broken apart. It doesn't have to break the H plus away from the A minus for this to react. So that's what happens initially. As you start to react that Na plus with the Na and the OH minus with this solution, this reaction is going to start. And it's going to start by attacking or reacting with the the ionized form of the acid. And what happens with the pH, so over here is going to be the volume of NaOH. So what happens with the pH is right away it immediately starts to go up, but then it kind of flattens out a little bit. And we're going to get into a lot more detail about this flat region. But anytime you have a weak acid, strong base titration in this case, the reason that it jumps up and then kind of flattens out is because basically that sodium hydroxide comes in and it starts to get rid of these. It starts to get rid of the H pluses and the A minuses. Okay? And then we keep adding more of this sodium hydroxide. Okay? And as we do that, what happens is all of the sodium hydroxide that we add gets used up, and it converts into, again, A minus and H2O. So as I start to add some NaOH, what's going to happen is these HAs are going to react. And what are they going to turn into again? They're going to turn into the conjugate base, the A minus. Okay, but notice we haven't really changed the hydrogen ion concentration. The hydroxides that are there, the OH minuses, remember this used to be HA. Those OH minuses react with the hydrogens to make water, so that doesn't change the pH very much. And the A minus doesn't change the pH very much. So as you get rid of all of those H pluses and A minuses, the reaction, the pH starts to level out. And slowly over time, all of this HA that's here, this OH minus is going to keep reacting with it, producing more and more of the conjugate base. Okay, so let's say that we, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say we started with 10 of these, okay? So slowly we're adding more and more of this. Again, let's just call it OH minus just because it's easier. We're going to slowly keep adding more and more of this to it. And as you add more of this HA is going to react and become A minus. Okay, and now we're going to keep adding more hydroxide. And you keep getting more of that conjugate base. But this whole time that this is happening, the volume of NaOH added, it's still, that pH stays pretty flat. Okay, it's going up a little bit, but not very much in this region. Okay, and that region is an important name, and we'll get there in a little bit. Okay, and eventually, I'm going to keep adding more base, and those acid particles, these HA particles, keep turning into more and more A minuses. Notice we get to a point where where exactly half of those HA particles, we had 10, we're left with 1, 2, 3, 4, 5. Okay, and now we have 5 of the conjugate base. We have a solution that contains, this is really important, pay attention to this part, we have a solution that contains an equal concentration of the acid and its conjugate base. Okay, and we're just going to say that line might be a little too long. Let's say we're right here, whatever that volume is. We're going to make a little point right there. Okay, and now we're going to keep going. Okay, but notice that again, half of those HA molecules are now gone and have converted into the conjugate base. Okay, and so we're going to keep adding more and more of that base. And as we do, more and more of those acid particles turn into the conjugate base. But still, again, the pH isn't going to change very much. Okay, and now we're starting to kind of run out of those acid molecules, and we're getting to the point where we're only going to have A minus left. Okay, we've got 2 left. So as we start to kind of reach that point where those acid particles are going to run out, you're going to start to see a slight increase in that pH. Okay, and then we're to the point now where we've only got 1 molecule left, and then that pH is really going to start going. And then when you get to that point where all of the acid particles are gone, what happens is you see a very quick and very fast rise in the pH. Okay, and it looks like this. Okay, because now all the acid, this is completely gone. There's no acid left. So when you continue to add more hydroxide to this solution that is completely filled with conjugate base, what happens with all those hydroxides? Nothing. So what do you have? You now start to get a bunch of hydroxides in here. And as you add more and more hydroxide, what does the pH do? It goes up. Okay? So right around, let's say here, we'll say is a pH of 7. And then basically you're going to keep adding base until you reach the pH of that solution, of this NaOH solution. And at that point, what does it do? It starts to flatten back out again. Okay? Now, this point here where you kind of see that point right where it's going straight, not straight up, but pretty close to straight up, where it goes up, the pH goes up really, really fast. And as you're doing this, the difference between here and here might be like 1 drop of NaOH. That's it. Or maybe 2 or 3. Very, very little of the base is needed to get from way, way, way below a pH of 7 to way, way above a pH of 7. Okay, now if you kind of look at this line right here and kind of find the midpoint of it, which I would say is right about there, that point right there, if you come down here, is what is called the equivalence point. Okay? And the equivalence point is the point at which, again, we saw it, as soon as those acid molecules are gone, as soon as all of these, remember these HAs that we started with, remember when all of those HA molecules are gone, that's when you've reached the equivalence point. It's when the moles of the acid that you started with, so the moles of the acid, and we're going to get into more detail with this once we start talking about this, equal the moles of the base that you've added. Okay? Because you started with a certain number of moles of acid in the solution, all of those acid particles, little by little over time, converted to conjugate bases, and at that exact point where all of those acid particles have converted into, and again, this is before you have any of those extra hydroxides in there, when all of those acid particles have now converted into conjugate base particles, now we're at the equivalence point. Okay? Now, whatever that point is, let's say it took us 20 milliliters to get there. Remember that point before, let's go back in time here a little bit. 1, 2, 3, 4, 5. Remember that point where we had half of those acid particles had reacted. So we had an exact same concentration. We have 5 HA particles and 5 A minus particles. And that's when we have, again, the concentration of the acid, the HA, and the concentration of the conjugate base are equal to each other. That's this point right here, which we call the half equivalence point. Okay, and that point's going to become a lot more important later on. Okay, so when you're halfway, when half of those acid particles have reacted, and now you have the same concentration of the acid as you do the conjugate base, you are at the half equivalence point. Okay, and what does that mean? Well, if it took you 20 milliliters to get to the equivalence point, what volume do you think it took to get to the half equivalence point? Of course, half as much, 10 milliliters. Okay? And so that is, and then again, as you continue to go up this curve, now basically when you're here, all you've really got in the solution at this point is a bunch of hydroxides and a bunch of that conjugate base, okay? Not together, obviously, separately. But once you're up to here, you now have a very, very high pH because, again, all of those acid particles are gone. And since all those acid particles are gone, you only are just adding more and more hydroxide to the solution, which makes the pH go up. Okay? And then remember, you've got this flat region right here, or a mostly flat region right there. The half equivalence point will always fall in that half equivalence point range. Okay, and that's a pretty common laboratory technique is when you're, and so now what we could do is we could say, okay, this NaOH that we added was, let's say again, 0.125 molar. Okay, what we could do is we could say, okay, we're going to use 0.125 molar and we're going to titrate it, or we're going to titrate the HA with that 0.125 molar sodium hydroxide. And it took us 20 milliliters to reach the half equivalence point. So we can use the concentration and we can use the volume it took to reach the half equivalence point to get the moles of the base. And remember, the equivalence point is where the moles of the base equal the moles of the acid. And so basically what you do with the titration, the whole goal of the titration is you're trying to figure out what's the concentration of that acid. So once you get the moles of the base, you use and we're going to talk about this in a little more detail right in the very next video. But you take the moles of the base from the volume that it took to get to the equivalence point and its concentration and get moles. And then you know that those moles equal the moles of the acid as long as there's a 1-to-1 ratio here in this balanced equation. And then once you have the moles of the acid, well, what volume of acid did you start with? Remember the very beginning, let's say you started with 50 milliliters of the acid. Well, then you would take the moles of the acid and put that over the volume, and then you would get the concentration of the acid. Again, don't worry about the mathematical part of that yet. I really just want you to understand the concept of why does the pH go up at the beginning and then flatten out? Okay, what does that half equivalence point mean? What does the equivalence point mean? We're going to go over all of this same stuff again in a little even more detail. But before we even started to talk about this, I kind of wanted to give you just something that you can imagine or visualize when you're talking about a titration.